Alright, so now that we have introduced the fundamental theorem of calculus, we can move on and we can look at one of the basic applications of the definite integral, which is in defining the average value of a function. Okay, so here is the definition. If you have an integrable function, so something where the integral exists over a closed interval, then you can define its average value by taking the integral from a to b and dividing by the length of an interval. Okay, and so this is, the best way to kind of think about this and realize that it makes sense is if we're thinking about something like, say, v of t being velocity or speed, with t between two times, say t0 and t1, we know that the integral from t0 to t1 v of t dt, this is going to give you your sort of total displacement, your distance. And so if you take so integrating the velocity is going to give you your distance traveled, and dividing by the time it took to travel that distance, which would be t1 minus t0, it gives you your average speed over that interval, right? So this is exactly what we're doing. We're doing averages, but we're considering it in context other than velocity and position. Alright, another way to kind of think about this and understand that this does give you some sort of average is to think of this as a continuous limit of the usual arithmetic average that you would see in a course on statistics or probability, right? So we know that if you have a bunch of values, for example, if I want to calculate the average grade for a test in this course, then what I do is I add up all of the grades for everyone in the course, so I add the total grade, and I divide by the number of students, or at least the number of students who wrote the test. That's going to give you the average value on that test, right? So you take the total sum of all the values, you divide by the number of values that there are. So if you think about a function defined with respect to some uniform partition, right? If you choose one point in each of your subintervals, you evaluate the function at each of these points, right? Then we know how to calculate the average of the function over each of those points. We just add up each of those values, then we divide by the number of points that we plugged in. That's going to give me the average. Now realize that if I were to multiply this whole thing by delta x, I would get the Riemann sum, right? The Riemann sum is just the sum of f of c1 up to f of cn, and I multiply each of them by delta x. We're using a uniform partition, so I can factor out the delta x. I can write it like that. That gives me my Riemann sum. The delta x is missing, so really I'm just dividing by delta x since it's not there. But also keep in mind that what is delta x? Delta x is just b minus a over n, and that means that 1 over delta x, which we see here, there's my 1 over delta x, right? It's on the bottom, right? 1 over delta x is n over b minus a. And so if I plug that value in for 1 over delta x, you can see that this n here will cancel with this n here, leave you with b minus a times the Riemann sum. And now if you take the limit as n goes to infinity, then of course on the right hand side, when we take the limit as n goes to infinity of the Riemann sum, what we get is exactly the integral. So this is one way to think about why this makes sense as a definition of average. It's sort of this limiting value, this continuous limit of the usual arithmetic average when you move from kind of a finite number of points to kind of a function which is continuously varying over some interval. Now, once you've defined average value, there's a theorem that comes along with this, the mean value theorem. And so the mean value theorem says that if you're dealing with a continuous function, then there always has to be somewhere on an interval where your function is equal to its average over that interval. And again, I mean, this is probably best understood in terms of, say, distance and velocity, right? if two people traveled, if two people started at the same point, ended at the same point, and one person sped up, slowed down, they decided they wanted to travel on that fast lane where speeds are kind of erratic, and so they're going really fast until there's someone in their way, and then they have to slow down, and they speed up, they slow down, they speed up, they slow down. Somebody else is traveling over in that right-hand lane, they just kind of take the slow and steady approach, and it turns out that that person moving at constant speed ends up traveling at the same speed as the other person's average. Well, then guess what? They are going to travel the same distance in the same time, right? So there's got to be some point C between A and B. There's got to be this point where if I were to take the average value, right? So this is going to be, well, what's the area of this rectangle? It's going to be f of C times b minus a. And so what we're saying is that the area of that one rectangle is going to be equal to the area under the curve, the area that I would get if I did the integral from a to b of f of x times dx, right? And so one way to think about the mean value theorem is it's telling you that in principle you could always get the exact value for your integral using a partition with a single rectangle if only you were able to choose that rectangle very carefully. You choose that point C where you evaluate your function to be this point where the function is equal to its average value, and then I guess you could get it. Why does the mean value theorem work? This mean value theorem for integrals? Well, it comes from the mean value theorem for derivatives. Right, so this comes from our previous mean value theorem. Right? So the first part of the fundamental theorem says that under the assumption that f is continuous, fundamental theorem of calculus part 1 says that we can consider this function, big F of x, is equal to the integral from a to x of f of t dt, and we know from FTC1 that this is continuous on the closed interval from a to b. We know that it's differentiable on the open interval from a to b, and so the mean value theorem then says, the original mean value theorem says that for some C between A and B, well, f of B minus f of A over B minus A should be equal to f prime of C. Okay, but now think about what do we have on the left-hand side. Well, notice that f of a is the integral from a to a. F of a is 0. F of b, well, f of b is just our integral from a to b of, well, f of t dt, which is the same thing as the integral of f of x dx. It doesn't matter what letter you use for your integration variable. And what's f prime of c? Well, FTC1 says that f prime of c is simply f of c. Okay, so the original mean value theorem together with the first part of the fundamental theorem of calculus gives us this mean value theorem for integrals. And this is something that you see popping up from time to time in the context of, let's say, physics, where you might be interested in problems like linear density, for example. You want to calculate center of mass, let's say, for an object that has non-constant density, non-uniform density. Well, you want to figure out the center of mass. You do that by averaging the density over the object. You'll find situations like this where you would be using this idea of the average value of a function, the mean value theorem, right? So the mean value theorem guarantees you that you could always find a center of mass, or do other calculations like this that show up in the sciences. Okay. So that's it for the theoretical stuff. We're going to move on to some practical stuff in the next couple of videos. We're going to look at how to do integration by substitution.